This one's going to be a bit of a faster one, but I was thinking about it because I got towards the end of the. It's actually Angela Caliestra or something like that, whose pulsar, this one weird trick for measuring the distance between them. And it has nothing to do with the measurement. It actually has to do with how to see more pulsars because there's an angular way that they ultimately, just push out light, right? But it's like, yeah, I mean, there's also light around there, of course. But if you know about the given, let's put it this way, the given directionality, I mean, there's 360 degrees of that, right? And so you know that. But considering where we are in our stationary area, which relative, it's not really stationary, but in that general gist of that direction, that means there's a 360 degree chance and likelihood of something being there that is not facing towards us, which isn't really the case, but it's sort of similar to that. And a way to generalize it is like, so knowing that and knowing the reflectivity index of different plasmas and knowing the fact that plasma can be heated up based upon those given types of electromagnetic movements and knowing that electromagnetic movements can curve in thanks to plasma ultimately gaining an electromagnetic field and that helping move photons, that makes it so that way we could do the really cool thing of knowing even greater amounts of multiple different areas of looking towards a given pulsar, get a higher resolution, but then also average out where and likely how many different angles of this pulsar frequency, of light, right, can be in terms of our galactic neighborhood. So we already have thousands of these things. And it's like there might be way more than we know how to look for. And a way to do that kind of looking is by doing this. We have the ability now to see something that isn't facing us and won't have light that ultimately reaches us. Okay? But it's like, well, pulsars still put out some light. And it's like, right. But now we have the ability to know if whether or not they are a pulsar that is not able to send its light to us and where that light is going and how ultimately that light can bounce back towards us, which isn't really a bounce back. Bouncing is not the right way to put that. It's more like light in a close enough way. It stimulates the, of course, plasma that eventually starts curving away because it creates an electromagnetic field, right? So, but we can also do something similar for reflectivity, diffraction, and refraction of any given area and look around and through nebula gases for frequency types that normally we would have said is a noise data point. And it's like, no, while they're diffuse, they're actually not noise. The only way they can come in towards us is if they're doing something like this and being interfered such that they are either going to a lower wavelength or a higher wavelength. Okay? That allows for it to be that we can look through these types of, interferences that are for the light that's trying to reach us, which is great. It also means that we're probably going to see a lot more that is there for what it's worth than we did before. Not just pulsars, but planets, possibly, they're close enough to another star that are able to, of course, reflect light properly to do this, or stars obscured by nebula gases. Plasma is a cool thing, but it is also one of those things where as it moves, as it shapes itself, as it does anything, it changes its frequency, of course. And then we end up understanding the basic kind of principle of that sort of stuff, where we have bunched up electromagnetic fields and elongated. And then we have the apparently constant, vacuum pressure and acceleration, which, it's probably slowed down because we're near like a gravitational source of energy. So I don't really feel like that's a good constant measurement in any aspect. But people debate that stuff. Personally, me, I'm like, you debate whether or not that's good? Why? How is it good? How does that make sense? That makes no sense. Anyways, I'm gonna move on because it's like, well, The other side of it is pretty quick in terms of like how you ultimately gain knowledge for curvature of light back towards us, but also curvature and multiple angles and interference pathways of light towards a given source that you are looking for in a given spot in a three-dimensional space, where it should have come from ultimately, because of course we have special relativity, as things will still move, but also all the rest of that, which then gives you a better understanding of really maybe some more of that dark matter and dark energy stuff, which is great, especially with the comets and asteroids that I am trying to, already kind of put up a video about that, except my internet's very slow and I just raw dogged it and put it out, and so that'll take for fucking ever. So there's that. But I was thinking about it because it was like, there's a lot more pulsars in terms of the 360-degree sphere and where they're angled, when they're angled, and what direction, along with travel throughout, of course, the galaxy or multiple galaxies that they could receive and enough of an angle and enough of a luminosity for us to sense. In terms of a nice little moment in time. It could look pretty darn bright for us, quite blue shifted, and we don't really maybe know why these fast radio bursts are a thing for certain things. And it's like, that could be a reason. You know what I mean? That could be a big reason, actually. Same thing for how much mass and energy in terms of how much collection of stellar intermedium, stuff like that, all happens to coincide with, greater increases of electromagnetic pull and repulse than we previously thought, and how significant it would have been, for those larger cosmic scales for things like that. And then it gets pretty complicated past that, but it's really just like angles and moments. So like you focus on one thing, you do multiple angles for that, and then you chunk it forward, and then chunk it forward, and chunk it forward. And like if you know the amount of different things that are around that area, and what could be, meaning expected values here, of what could be, and what should be, and what we do know, and what we have theorized, and that's programming, of course, for your sensor, right, and for the data that's there. Then you're able to work it forward to the point where you can look at this thing a little bit more clearly and possibly see something that you didn't see before, which would be amazing. And, that means there's probably more pulsars than we expect, but also a lot more stars that are just not quite that bright. You know what I mean? Like this is one of those things where like we made a calculations for our calculations, several of them, for a given observation that is lackluster. Okay, and so then when you add in more of that with both more possible neutron density because of this, more light wave interference, and the elongation along one side versus the compression on another, and it creates more luminosity on the direction that it's traveling away from versus towards, that increase, of course, its speed, but also the degree of condensation. That's a thermodynamic effect. So it's like it spent energy, and then it ultimately took up chaotic, non-ordered ways of movement, which is, thermodynamic speak for suck it got colder. And so it pumped itself that way, right? So, but when you know about electromagnetics and the fact that plasma happens to work with that along with photons, it then makes it so that way it becomes more actually applicable for that. And these larger scales, especially as things are spinning and moving, right? So, anyways, that's another thing. But it's like, it's all these little chunkety details that effectively mean we could be incredibly incorrect for the total amount of mass that we actually know in no way right now is there. But we theorize is there, but we don't have good theories because we don't have good measurements. I mean, it just gets worse from there. So there's that kind of stuff. So yeah. Right, so this is the beginning of another one, because I still haven't finished the video. I'm basically at 2304 is what it says up there. Anyways, point is, It's like, oh, so interstellar medium for big old nebula, which is a Faraday effect for her, right? And I'm like, yeah, it depends, really, realistically, on what we're talking about for the movement, the shape of that given plasma, because that's a big deal and it has a massive impact, especially with vortices and the different charge variables, because we're talking about electrostatic forces now too, and how it can also influence both the movement of that plasma, but also the movement of, while it creates an electromagnetic, but also creates a is it electron plasma, I guess, in a way, is to look at it. But what that means is it creates a very large Hall effect, right? And so that makes it so they can even elicit their own types of photons, and they'll actually try and kind of reduce their overall movement. That's an entropytic effect in thermodynamics and the quantum kind of space of things. But what it means is it's like, oh, I'll elicit a new photon and I'll get more photons, right? So it depends. It's conceivable that it very much just like Faraday affects the entire thing. But that's not really what I was thinking about. But it made me immediately go, well, not really immediately, but pretty close to that, go, wait a second, there'd be a hell of a lot more light in like a lot of intergalactic space. There'd be a fuck ton more light. Like way more light than we think. Like a tremendous amount more, to the point where it'd be dangerous to us in all aspects. Like to the point where it'd be a lot more heat than we're thinking there is in galaxies and around galaxies. Like we'd be very hard pressed to actually know, because of course we have our own Faraday effect interstellar medium called the Oort cloud, to the Kuiper belt, whatever it is, to then also the regular electromagnetic magnetospheres of multiple planets, and then the star, and then of course light pressure pushing against that light coming towards us. So as it gets closer to us, and we're relatively speaking pretty close to the sun, then it gets even worse. Like the further and further you travel away, while yes, our star protects us, once you get past a point, then you're going to have the very opposite. You'll have far more of light that escaped, to ultimately becoming quite filled, I guess, in a way to think about it. Like very luminous in a manner of speaking, except it's not really quite like that. Okay, like a good way to put it is like we have this gravitational field and we have a bunch of shit coming towards us, and that of course changes our observation point. Special relativity makes it so that way we understand it as a curvature, as a lens. But in reality, when there's 360 degrees and there's a bunch of light wave interference and there's a bunch of electromagnetic magnetospheres for that given Oort cloud, but also from around where the Kuiper belt, whatever it is, ultimately creates its own version of an interference pathway towards us, right? But that's the thing. In between things, while for us in our angle of incidence, as it of course kind of compresses, lenses the light that's heading towards us, it doesn't have that really anymore, right? So it'll start heading towards filaments that are already there, which of course is the dark matter, dark energy stuff. But then there's stuff that's like, well, I'm just going to scatter, right? So it's like a bunch of extra light that's everywhere, and a lot more electromagnetic field propagation. In a sense, it's not really, I wouldn't say it like that. A good way to put it is like pulses of electromagnetic frequencies that are kind of like EMP pulses, electromagnetic pulses, right? From like a nuke. But like that's only because they're wrapping on massively larger fields and scales, and of course they drain energy into things and as they continue on, right? But what that means is it forces movement. That's what that is, right? And so that movement then of course is going to more likely, because of entropy, head in the direction it's already trying to head in, right? That's Newton's law, but also entropy, of course. Then we end up like kind of having to deal with light that is different than we think, right? Like light from the Big Bang as a source would be vastly different We think it's redshifted quite significantly, and it would be. It has to be. But it's also, yeah, it also got compressed multiple times, meaning blue shifted, this wavelength, right? Along multiple gravitational axes, and then amplified along multiple plasma pathways, right? And along with a lot of others, which then changes its given type of gravitational influence, which isn't like gravitational influence on light. It's more gravitational influence about how it gets lensed towards us. Think it got spread out to a much, much larger, it's like, oh, it's this little tiny hole right here, right? But it's like, no, actually it's the entire wall. And then several different things all tried to effectively hit right around where that would be, right? So, and throughout multiple versions of that, of course, it creates another outward, inward, and directionality as it continues to pulse towards us, right? So it's kind of like a multitude of different pathways, gravitationally speaking, that it would take. And gravitational lensing would be an incorrect way to effectively try and look at something for distance, because it wouldn't accurately give you any kind of picture, because light wave interference will both constructively and destructively interfere, and decay speeds for different plasmas or speed them up, and so on with electrons, and of course whether or not they still exist around, and the quantum foam, right? So like it'll bunch up pockets of quantum foam and keep it around for a little bit because of how far away that is. So it's one of those things where it's like, yeah, no, it's actually going to curve differently than we think and expect, and the given numbers she was running were really far off, which is to be expected. But it's also like, we got a way to now look at things really further away, way more accurately, while also understanding that it's like we might actually not understand how much further away we really are looking, or where we're looking. Like, we might be looking towards this thing for the James Webb Telescope, but and it might genuinely be that type of light that because I guess an infinite variability of angle is what light does when it's at a luminosity kind of like that. But that kind of like begs the question why we do that kind of like type of calculation, because of course it spreads, right? So that doesn't really make sense. You know what I mean? But it's like, within that context, it would create enough photons that would still get to us. But there's going to be so many chances. Like, these would be enormously slim chances. So it's very likely the noise data is something that we can fully kind of piece out, and figure out how to remove, but also how to gain more, and really actually know how much of that noise data is either something that is that we're trying to look at, or that we're not, right? It's also like, how much brighter would that become, right? And then that's predictive analysis, which isn't totally predictive analysis, but there's a degree of that. Of course, eventually we'll get there no matter what. Like, no, there's so much worry. Shut up. Do some fucking math. Shut up. I don't care. Do the math. Do progress over time. Stop it. Stop trying to cheese. You're like, no, it's good. No, it's not. It's not. Shut up. It's so much math. Yeah, it is. Kind of. You'll get better. It'll just be chunks of various, like, new fucking symbols and whatever the fuck, and you'll be like, it means this, roughly. You know what I mean? So it's like, whatever, I don't care. Do the math. You want to get the chunk so that way you know what it is, then fucking do the math. You're going to do the math to get the chunks, and everybody will get the new chunk, like fucking letter, number, whatever the fuck it is, symbol stuff. And then you'll be like, I'm the one with the name. It's the Lemke symbol for this. It's John Tyler Lemke here. He discovered that thing. Right? Anyways, as you're all trying to do, I guess. Anyways, moving on. Of course, that really also begs the question, how much is that not what we think it is? is that something that got interfered and angled enough times to ultimately be seen by us, but was not actually the Big Bang light, or near where we think it is? That's my problem. It should still be there like that, but it's like, how much of it isn't that? Because we're looking at these minuscule, tiny things that could genuinely be a jutted out direction and merged together of photons that are fully not what we think we're looking at. And that becomes a problem. Because then it turns into, well, I mean, you got the Big Bang that very likely would have had such density, it would have formed to some degree of black holes and supermassive black holes, as they, of course, would have gravitationally attracted each other and even became inside of other stars and so on, right? And, created stars as a result of that. That's from pretty much the beginning of the universe, but then it's like, how much is the question? But also, how bad, are our initial assumptions? And because everything's angling and it goes backwards, it does this, and it's like, yeah. Do we know that that's the case now? We know it's going back. We know that. Okay, we do know that. But what actual, is it like a wall? Is it more of a point? Or is it like, actually it's kind of like a cone? Or is it like several other things similar to that? But, if you all eventually get it to, and then it's like, no, it's back to a ball again. But might have been shit out of luck on that fucking theory. At the first start, you know what I mean? To like, oh no, it was some weird wall. What the fuck? How big was the Big Bang? How big was this? It's big. Okay. It was infinite. I can't see that size of a fucking. How big was it? Where did it go? I want to know. I need to see it. You know what I mean? It's the thing. But it's like, there's no way that this isn't going on. Okay? Just FYI. There's no way it's not. All right? But at the same time, it's like, I can guarantee you there's a bunch of astronomers who are like, we're doing this. And I'm like, yeah, no, but that would mean that you'd said it in every single one of your fucking stupid studies, in your little observations, which you didn't do. You know what I mean? That's the point. Looking at these chunks of interference pathways, looking at these types of, and all the rest of gravitational, electrostatic, electromagnetic, Faraday, and non-Faraday, which turns into amplifatory, because it makes more light that's effectively entangled, being the same light, right? Same wavelength, same light, right? And so it's not technically entanglement, but it's kind of like that. Because we're talking about between 2 points of an electron, but also we're talking about movement of an electron as it, technically doesn't view itself as not attached to something. But that's quantum stuff. And so as it's moving and it's being repulsed by other electrons, it's still attached in its mind by something, which means it decays back towards that something, which makes another photon, right? And it will be of a very similar wavelength because, of course, as it travels, it, of course, creates enough energy to make a very similar wavelength, right? So, and then you end up having the other lensing and then mass and then movement of particle through a given type of thing. It's the whole thing. So, you end up going through a lot of those calculations, but it'd be necessary. Your microwave background whole map would be wrong, in every aspect, actually, which sucks. It's like, no. Remember that thing we've been saying is a thing? It's not. There are all the stuff that we know. Well, we for sure do. Okay? Don't even. Don't. I see you over there trying with this magical bullshit now. Fuck you. Absolutely garbage. Science is real. Stop it. On the other side of it, we're going to have to do some more calculations and really kind of tease out how much it is that we're viewing what we're viewing and how it is that we're viewing it. It will very likely, for close stuff, give us better accuracy and resolution and clarity to ultimately not just distance, but what it looks like and planets around it, if they're there, interstellar medium, asteroids, comets, all of that stuff. But the further away it gets, of course, the more likelihood chance there are more interference pathways that made it so we don't have that right. And we're looking at something that might not be where we think it is. And that will tease out a lot more information and it'll become a lot more accurate, I suppose. Like less obscure and better, really, for us to make better, more accurate predictions moving forward. Which is great. I'm not in any way that person that goes, no, we didn't see farther back. No, I just don't know if we saw that far back or if we saw that specific thing actually where we think it is. Because that's light that can also be curved backwards and headed towards us over the given distance and time we're talking about. Which is like, we saw this thing at the rear to us if we were to look at it, but we don't know that we're looking at that thing over there like this, but actually because it went over, we're thinking that that rear is actually the front of something when it's not. Which would be bad news for us, right? Like our measurements would be very far off. And that would suck. And there's no way it's not there. That's also another problem. So how bad is our current assumption of it working backwards is what that initial thought process and question I posit is. How bad is it? And the answer, unfortunately, is very likely to be quite bad the further back we go. Which is bad. Quite bad turns into, this is about 80%. This is quite bad. Yeah, this is quite fucking, this is Wild West of the astronomy here, plus or minus 80% of what we thought we saw is not there. Or it was way more full, we just didn't know. Right? Or we thought we were seeing this thing. Actually, it's not that thing that we were looking at. It was something else over here. Ooh. And it's like, no, I mean, not always, but a good amount. Right? And that's kind of shitty. But also fucking phenomenal and great because now we have like a brand new way of effectively teasing out all the information that we need to make it so we know and we can shove it in those damn fucking denying ass bastards' faces right there. Fucking suck it. We did it so fucking well you can't possibly. There's no fucking way. There's nothing else there. Ha. Some fucking person going, I know the world is this, and it is, of course, the very definition of why creationism, because it was created, blah, blah. Because we did not know this thing. No, I mean, a little, a smidge, but, no, it's not going to result in that. It's very unlikely to result in this. Are you kidding? For what it's worth. Yeah, it's like, and we might be able to tease out better stuff that would be there, that we didn't see before. But also, we're not talking like, man, there's an alien there, or alien race that got a big old screen that's around the entirety of our Oort cloud or some shit. That's like feeding us little fucking, photons and shit like that. Like that, you know what I mean? It's still scary as a thought because it's like aliens could theoretically do that if they were high enough and advanced enough. We would never know. They're never going to get to the Oort cloud. These fuckers are probably going to kill themselves, you know what I mean? They're over there just fucking, look at this stupid cunt trying to think he's going to get over there. Right, I'm just going to go over there to the Oort cloud. He doesn't even know how fucking far away that is. Oh, shit. The moon! We're going to the moon! Way closer, we got to the moon because it's hard to do. That's right. So, just a thought I had that sometimes keeps me up just a little bit. There's nothing saying that there can be a second generation alien race species that happen to, evolve, be intelligent, and then eventually do something like that, and we're just one big experiment to them, I guess, or just a zoo or something, which is a disturbing thing. But anyways, if they did do that, it's like, well, then they want us to know about evolution. They want us to know about a lot of this stuff, and we would eventually get there too, which is a whole other thing, because it's like even creationism, when it's like, oh, they can pop thing. It's like, yeah, but they still want us to think like this, which would mean that for sure, even if it was a thing, you should probably go along with that kind of thing, right? Like, no matter what, that's definitely a thing there, whatever this is right here. So I never really saw that as being like a valid argument at all, right? But, far be it from me to have people no longer have as much power and authority over others, and their belief system is making it so that way they don't actually do certain things that they're uncomfortable with, right? But I'm going to move on, because, see you later, right? In terms of like signing out, because holy shit, are you kidding? Like, this would be insane to think about in a lot of ways, but we'd be able to see that. Not really. Like, honestly speaking, they could have like a tiny little in the like quantum realm of like movement of particles and photons, and it's just actually a screen there, and then you're just going through it, and you're all holographic superpositional collapse computer guy going through actual stuff, and you just think that there's something that isn't there. Why would you say that? I don't know, but it's a possibility, and they're not that endless. I'm just saying, with their current understanding of physics, this is very possible. And yes, you might want to just do the human race equivalent of, we're racing to effectively make sure that this is not a thing and we're living in the real place. Because they're like, no, they would do stuff to us. And like, you don't know if they are or aren't. And really, there's the other side of it where it turns into... they could just be like us filming in the planet Earth thing, which is very meta in a sense, and they just let you do whatever. Which is disturbing, I guess. Just fucking like, let me fucking hurt myself. Yeah, in the grand scheme, what are you really to them? Right? Anyways, moving on. But the point is, it's like, if you scale this out, they have to then make it so that way you see what the beginning would be. No matter what. Okay, so like that's a thing you're gonna have to do. Yeah, fuck whatever that is. And over here, let's focus here. Come on, let's focus. It's a little bit. Oh my God, my fucking Jesus, fuck. What is it that we're doing over here now? Oh, we're just trying to tease out reality. What the fuck is we are and what's going on. Oh my fucking God. Scary, existential. Not really, when you think about it. But it is kind of a little bit. Once you get there, you'll understand all the things. It's what that tends to be. Sort of situation. But yeah, that's the whole point that I end up thinking about, where it's like, okay, so with this, we at least know how to knock out the idea of Big Bang being one specific type, and how our universe is this one or that one specific type, and we can go beyond what we believe our observable would be, and our theories can then get honed in to more accurate predictions, but also likelihood, right, for age, and so on, for depth and more, which is great. And then same thing for what might actually be out there, what we might not be seeing, right? And where things might actually be, and how much quantum physics plays a real role, because it's got to be everywhere, and how much we see that quantum arena play in terms of the dark matter and dark energy. Same thing for light wave propagation and prevention of light over distance. We think it's like so not like as thick and just soupy. Like we're talking chunky. If it had mass, my goodness, right? But it's like, of course it's going to interact with things that have mass. Of course it's going to do things. It's so thick. That light that's there has to be massive. It's got to be so much extra energy than we ever really think it is. And that's amazing to me, because as we move forward, of course, that's going to change things. It's going to dump energy into us. It's got to go somewhere, right? It's got to do a lot more than we think it might be. And that's pretty awesome. It's a profound thought. If we were ever to go from our planet to another planet, or from our galaxy to another galaxy, we would have to factor in those equations of how much light wave energy there could possibly be that could interfere with us and damage us, and possibly not do that, right? So it's a cruel thought. Like, if we were ever to become a galactic species, we need to know this. We need to know how much light there really is. We really need to know. We need to know how much interstellar. We need to know a lot more about that, you know? And it's like, man, there could be a lot more light there. And there could be a lot more mass there than we thought previously, just because of how small those little things could be. Those add up massively, not just like chunks that are the size of even my body. I'm talking like little bitty bitty peas down to like dusty dustas. You know what I mean? Like, that's everywhere. There's no way it's not. And yet light's going through that. And it's hitting some of it, and some of it, it's just going right through. Crazy, really, when you think about it. Because we already know about like how to use a lens and multiple mirroring systems with like a little dust, but it's really just placed kind of like mirrors and lenses in a given area that then focus more light towards a given sensor and detector, right? Like, we already know that in low Earth or, you know, Lagrange point area, you know, for telescopes. It's like, if you think about that, it's like, behold the universe on another scale, bitch. You thought. You think you know, you didn't know. Boom. And then you're just like, I'm small. I'm so small and insignificant. You know what I mean? Anyways, see ya. Bye.